Hello everybody, so we are back again to our plasma class. In this class, we'll be starting on the designing plasma torches and finding how to determine its electrothermal efficiency and gate characteristics. So, in our previous class, we already started this one and we told that um, uh, a plasma torch, how it operates. There is a cathode, there is an anode, and this anode is having cooling, and this cathode is also having cooling on the back side. An arc is established between the cathode and the anode. That arc hits the gas that is flowing, and the plasma jet is formed. Now, when I am coming to the electrothermal efficiency, uh, how it is defined. It is defined as the total electrical power input that you get, multiplying by the arc voltage by the current that is flowing. Arc voltage means the voltage that is between the cathode and the anode that you have measured. So, that is the voltage, and usually, as you know, this is operated using a constant current power supply unit. So, if you multiply the voltage and the current, then you get the total power that you have supplied electrically. So, you note that. So, this is the electrical power input. Now, the question is whether the whole power is getting into the plasma or not, or some part of that is getting lost. So, that is very important to know because that will determine the efficiency. So, power that is going into the plasma divided by the electrical power input multiplied by 100, that will give you the efficiency of the plasma device. Now, why the plasma power should be less than the power that you have dumped using your power supply? The reason is that to save the structural integrity of this cathode or the anode, you need to cool them intensely, because this current density over the cathode is tremendous, of the order of 10 to the power 8 per meter square, ampere per meter square. Now, for that high current density, the J square by sigma heating is so intense that unless and until you are able to extract the heat, keep the temperature of the material below the melting point, the material will simply melt in few minutes. So, cooling is a must to save the structural integrity of the electrodes. If that is the case, then it is obvious that you are extracting the heat from the cathode using cooling water or something. So, temperature of the cooling water is increasing. Now, suppose the cooling water which is passing through that uh, enters with the temperature of T1, and after cooling that thing, its temperature rises and say comes out with a temperature T2. Then, if M is the mass flow rate of the coolant, S is the specific heat, and delta T is T2 minus T1 is the temperature rise, then Ms delta T will give you the amount of energy lost per unit time through the cooling channel. So, it is very easy to calculate from the rise in temperature of the coolant as it passes through the device. Similarly, for cathode you need a cooling. If you have additional segments downward, that also should have a cooling. So, the more the number of segments, more cooling you required, more amount of heat is extracted through the water. So, that is a loss. So, if you are considering this kind of torch, I will tell you that there are two different types of torches. One is your transfer arc and this is a non-transfer arc. So, those things are there. So, this is a non-transfer arc kind of thing. Now, here if you are trying to calculate the efficiency of this device, then in this particular device there is only two segments. One is your cathode, one is your anode. So, the whatever the heat is being extracted is only through these two components, and input is V into I. So, the amount that is extracted is limited to this only two components. But if you are introducing number of segments, then naturally the amount of heat extracted through that will be lost, and basically you are helpless. You need to give them cooling. If you didn't give them cooling, then you know that efficiency will increase because you have not extracted heat. But at the same time, temperature of the components will increase and that will melt them. So you are forced to give them cooling, and that way you are reducing the efficiency because whatever the heat is dumped, you are extracting through the cooling channel. Now there is another kind of torch which is called transfer arc. There you really don't need additional segment. You directly connect that arc to the, this arc, you directly connect that to the job. So in that case what happens? Because no other segment is there, their efficiency becomes very high. So this kind of devices which is this non-transferred kind of thing where the arc is not connected to job, there the efficiency is quite less. So typically that efficiency can range from 40% to anywhere, and you can, if you design very efficiently, it can go even up to say 70 to 80%, but not more than that. It's very difficult to get it. But if you are going for this transfer arc, then the business is between the cathode and the job, and rest of the parts basically isolated, and no heat is extracted through them, and the heat that is dumped over the job, that is a requirement. For example, if you are using a melting furnace, there you need to connect that arc to the job to melt it. So you want to deliver the maximum amount of heat over there. So in case of transfer arc, you easily get an efficiency which is greater than 90%. But that is not possible with the transfer arcs. So what are the different channels through which the heat transfer takes place? When you are considering this cathode, they are conduction, convection, radiation, and then there are another two. This is electron emission. This is a very particular property of your cathode, and then ion bombardment, because cathode is negative, so ions get attracted towards that naturally because of the electrostatic force and bombards it. So that way it transfers its energy to the cathode. Okay, so that is another way of heat transfer process in the cathode. When you are coming to the anode, this one, so what are the different processes? So they are Joule heating, because current is anyway going there through that and then coming to the ground. Now electronic heat transfer, then radiation, then conduction, then convection. So only thing that is not having over there is that this ion bombardment and this electron emission. Why they are not there? Because cathode is at positive potential, so electron will enter there. So electronic heat transfer is there, like this ion bombardment kind of thing. Electronic heat transfer, because electrons are anyway entering there, but ions are not reaching there. So that is why ion bombardment is not there. Now Joule heating is of course there, same as before. Conduction is there, then radiation, because if it is hot it will be doing there. So these are the differences what you are seeing, this top and bottom. So in one you are getting ion bombardment, in another you are getting electronic heat transfer, but not the ion bombardment. And electron emission is not a property of this cathode, anode. So this term is not there. Okay, so these are the different aspects for cathode heat transfer and anode heat transfer. So we should keep them in mind. And I have explained to you what are the causes for enhancing or enhancing the efficiency, and what are the things that affect the efficiency of a plasma device. So you can do the simulation as usual using a property code and a fluid dynamic code. I have explained it well in previous classes. So here I am just showing you one where this is a cathode, and here, unlike the cutting torches, we have used a 5 mm diameter. So this is a common plasma device which can be used for waste gasification or other applications. Here what we are getting the distributions, because now we are having a bigger diameter, instead of 28,000, 30,000 degree Kelvin, we are now getting a bit less. 24,000 degree Kelvin is the maximum temperature over here, and that is, it is less by 6,000 compared to the cutting torch. It is expected. Similarly, you can get everything, this ion distribution, your pressure distribution over here, and this is the potential distribution. So this you can directly measure, and this is the axial velocity distribution, and this is the current density distribution. So they are having the typical features of converging diverging pattern, and this velocity here, unlike your cutting torches, because of the narrow diameter, the velocity is quite low. Here it is around 4,500 meter per second, but that is also quite high. So here it is a vivid, more clear picture about the this temperature and velocity, pressure and potential. So you can have a 2D plot here, and how we are calculating the efficiency, that I will try to explain here, okay, from the simulation itself. So you know that u is the axial velocity. So with this velocity the jet is coming out, okay. Now u is the velocity, number of amount of distance it travels in 1 second, okay. Now 2 pi r into dr, this 2 pi into r into dr, that is constructing a cylindrical cell of thickness dr, and there the velocity, axial velocity is ur, okay. So this 2 pi r dr, that will give you an area, and when you multiply that by the velocity, that gives you the volume covered by the plasma in 1 second as it is flowing out, okay. Now what is the density over there? Rho. So if you multiply that volume by rho, you are getting what? You are getting the mass in kg, okay. So the amount of mass that is coming out through that elementary cylindrical channel per second is given by 2 pi rho u r dr. So that is the mass that is coming out. Now what is the joule content of that mass which is coming out? So enthalpy, that we know from the temperature, because this temperature distribution will give us the enthalpy of the plasma fluid in that annular cell between r and r plus dr. So the amount of, if we mass we know that is coming out from that cell per second. Now if we multiply that by enthalpy, what is enthalpy? It is joule per kg, and how much kg that has come out per second, that we know. So if we multiply that mass with this enthalpy, then we are getting how much joule that is coming out from that per second, okay. So that is basically giving you the energy that is coming out per second through that annular channel between r and r plus dr. Now if you integrate that from r equal to 0 to capital R, so that is the whole volume of the cylinder, this integration will give you the total amount of energy that is coming out through the plasma per second. So that is the power of the plasma itself, okay. So the numerator here gives you the amount of power of the plasma that is coming out, and V arc into I arc, that gives you the electrical input that you have applied there. So when you multiply this ratio by 100, you are getting the efficiency of the plasma torch. So in this exercise, what we have now understood? We have understood that from the simulation we can get the distribution of temperature. From that we can know the distribution of enthalpy. We know the velocity distribution from the simulation itself. When we do this integration in that computational domain, we get the amount of energy from the plasma that is coming out per second. So that is the efficiency of the plasma itself. And when we divide that by electrical energy input, that is V into I, then when we multiply the whole quantity into by 100 into 100 with 100, then we get what? The efficiency of the plasma device. So that is how from simulation itself we are able to determine what is the efficiency of a plasma device that we have just taken into the simulation. So for the design, this will be my efficiency. So if we are not happy with that, we will change the design and we will do the complete simulation. Again we will calculate what is the efficiency of the device. So this is the way you can understand that we can design different types of devices and we can find out their efficiency. So which fits the best for our application, we will choose that, right? So we can do that in a very intelligent way. And when I am changing that, I want to change the design of the device, you are probably not sure what exactly change I am talking about. Okay, so for that I will just give you some example. Okay, so here what I am doing, that I am doing with different gases. You see, once I have put N2 is to O2 as 20 is to 80. So that is not the common air ratio. And another case I am using N2 is to O2 is the 80 is to 20. So that is very close to the air composition. So if I do that, then what I am seeing, that there is a difference in the temperature, but not much. Okay, there is a difference in the velocity, again that is not very huge, but what I am seeing, that if I use the same design and if I operate with air like 80 to 20 ratio, or if I operate with a reverse composition like 20 to 80, I am seeing that there is not much difference. There is a difference, but not much. Like here you are seeing that velocity has gone to 4500 when I am using 80 to 20, but when I am just using the reverse composition like 20 to 80, then I am getting a lower velocity. So it is around 250 meter per second less. Here temperature is difference temperature distribution is almost similar in the both the two cases. So we can predict that if you are changing the gas, that is the plasma gas, then this is the kind of effect you are going to have. Then here I am showing that when you are changing the nozzle design, so when I am saying that if you go for a different design, so here I have used a straight nozzle, here I have used a converging then diverging nozzle. Okay, so and you can see that the significant difference in the distribution of temperature from this to this. You see that here there is a monotonic decrease kind of thing, and here you are seeing that you are able to confine the high temperature zone here, and what you are seeing, that the temperature in the zone where it is expanding is less because of the expansion, and you are getting rather a wider volume of plasma here. Okay, so that is the kind of thing you are getting over here. And when I am changing this kind of distribution, then what you are seeing, the drastic change in the velocity. In case of a straight nozzle, this kind of thing, you are seeing that you are getting a lower velocity, but because here you are made it to converge like that. So that is causing a sharp increase in the velocity in the central zone. You see over here. So because of that only, you are getting a much higher velocity. So if a process requires a higher velocity for to reduce the interaction time or something like that, or to increase the productivity, then you may go for this kind of design. To enhance the velocity of the plasma jet at the central zone, you can use a converging diverging kind of nozzle. And what you are seeing, that this is also having a good impact on the temperature distribution. So the lower one, you are seeing that the temperature has dropped down. So although you have got a higher velocity, your temperature is reduced in the exit plasma channel. Whereas in the previous case straight nozzle, your velocity was less, but you had a higher temperature over here. So this is how you can predict that how a different design can result in a different type of distribution, and how the distribution will look like, whether that is favorable for the process that you are going to do, or you need to change it some other way. So that is how the nozzle design basically affecting the scenario in a much more prominent way compared to what happened when you were just changing the gas. So, changing a device geometry has a immense impact on the plasma jet characteristic that is coming out, because it is able to shape the electromagnetic body forces in a significant way, and that is how it is basically shaping the behavior of a current carrying fluid like plasma jet. Okay. Now, in this actually just I wanted to show you that when you are changing the geometry, how the simulation proceeds, because you have already seen the simulation that we have shown earlier, how they proceed. And here, because we have now changed the geometry, it is a straight nozzle but a much higher diameter nozzle, and how the simulation proceeds you just see here. See, previously you have seen that it was quickly converging. Now, when we have increased the diameter, then it initially showed a much wider, jumping in the solution, and then as you proceed, then you see that it is now here in the beginning, and here still certain certain oscillations are there, but as you proceed further and further, you see that the things are still oscillating, but more or less a converged kind of solution. Sorry, so it has gone there actually initially, and here you are coming over here, and you see that it is more or less now a steady solution. But the thermal equilibrium, if I stop it over here, you see that the thermal equilibrium is much better here. Earlier, what we are seeing, that electron temperature was quite high in this zone, and the asymmetry between the heavy particle temperature distribution and that of the your electron temperature distribution was significant in this zone actually. Now, here you can see that most of the zone are now thermalized. So, this, when you are increasing the diameter of a plasma torch, the plasma temperature distribution or the device is offering you a plasma jet which is more thermal, you can say. And here in this zone actually it is almost the temperature distribution is this R and this R. This is the heavy species temperature and this is the your electron temperature. The difference is quite less now. It is so, it is you can say that it is a more thermal kind of device. So, in this actually what I will explain you, that so far what we have understood, that how simulation can lead to design without actually making the device, and that saves your time and cost. Now, how an actual plasma jet behaves. So, they are basically the things. Now, what I will show you, different plasma devices here. This is a plasma torch which is discharging nitrogen plasma jet. So, this is a nitrogen plasma torch. This one is an argon plasma jet. This is a RF plasma torch, and you can see that the camera is moving, but inside this is a plasma. It looks like as if it is a static medium. So, it is so stable. But here what you are seeing, that the air plasma jet is jumping from here to here, and that jumping is continuing. It is sometimes so long that it is hitting the floor from the top of a table, but many of the times it is jumping back to a shorter length. Now, I will show you that when this this nitrogen plasma jet it runs, you see that how the jet behaves. Okay, and this is an argon plasma jet. When it runs, you see that it is running. Now in front of you there are 4 jets. One is argon plasma jet, one is nitrogen plasma jet, one is radio frequency produced argon plasma jet, and one is air plasma jet. So, the behavior is significantly different, right? as I told you, the air plasma jet is showing lots of instabilities, and the point to note is that the operating conditions. You know the set current, because these are operated using your constant current power supply. So, the current that you are pushing is fixed. The flow rate of air through the inlet, that is also fixed. Geometry is fixed, and you know that power supply behavior is also fixed. So, current is fixed, your gas flow rate is fixed, gas is fixed, geometry is fixed, everything is fixed. But still, what you are seeing that the plasma jet is oscillating enough. It is showing lots of instabilities. So, what is the origin of these instabilities? So, that is a very important thing, that is an important question which you need to answer. Why? I will just give you a simple example. Suppose you are introducing a process gas in this zone. So, you are seeing that sometimes the jet is very much over here. So, the process gas or whatever process material is there, they are interacting with the plasma jet. But when it is taken back, then there is no plasma, so it is not getting processed. So, if you are using this jet and keeping your item to be processed at a zone here, then sometimes it may interact, sometimes it may not interact. On the other hand, if you are putting the same thing over here, it will be facing a very high temperature, but at the same time it will be getting the plasma jet all the time over here. So, it will be affecting the process. So, it is very much it is very much needed to understand why this kind of oscillations happen in plasma jet when rest of the parameters is constant. So, that part we will be understanding in the later classes. And the other thing is that when you are switching from this air to argon, and you see that argon plasma jet is almost static, there is no such fluctuation at all is there. So, whatever you are seeing, a major cause of such instabilities may be the gas itself. Here you are using a molecular gas, and which is able to produce the electromagnetic body forces in such a way that the plasma is so elongated. You see, it is coming out like a sword. Here in this, actually we are using an argon plasma jet. So, the electromagnetic body forces are received because the ionization scenario is different, ionization potential of the gas is different. So, the concentration of electrons and ions, their properties, the properties of the plasma itself is different. So, they are creating an environment where you are able to get a jet with much lower instabilities. On the other hand, if you are going for air, the properties itself, they are connected in such a nonlinear manner that they are supporting this kind of instabilities in air plasma devices. On the other hand, when you are going for nitrogen plasma, you see that the distance is quite less compared to this one. So, it is not a free jet, it is impinging on some calorimeter here actually. You need to put your process material or whatever the process item over here, and still you are seeing that some instabilities are originating at some point. This last one is an RF plasma produced jet. So, some 3 megahertz 3 kilovolt supply has been used to generate this plasma, and it is very static and stable plasma jet. So, all these are depending on the kind of gas that you are used, kind of mechanism that you have used to produce the plasma, and the kind of geometry that you have used to get those plasma jet in that device. So, we will discuss more on this in the classes that will come, and I stop today here. We will meet you in the next class.